Something is awry in our understanding of the universe. Cosmology seems to be heading for a showdown on one of its most basic questions. How fast is the universe expanding? For more than a decade, two types of measurements have been in disagreement. Observations of the current universe typically find the rate of expansion, known as the Hubble constant, to be about 9% faster than predictions based on early universe data. Researchers hoped that the James Webb Space Telescope, the most advanced telescope ever built, would help settle the question once and for all. But consensus has so far failed to materialize. Instead, the Space Observatory has cemented the discrepancy with stunningly precise new observations that threaten to upend the standard model of cosmology. The new physics needed to modify or even replace the 40-year-old theory is now a topic of debate. An exciting and interesting possibility is that there's something we don't understand about the universe. Join us as we dig deep into how new ultra-deep images from James Webb just confirmed there is something seriously wrong with our understanding of the universe. Our universe started with a bang, the Big Bang. Energy, mass, and space flashed into existence all within a fleeting instant. Then the young cosmos was formed, an expanding roiling plasma broth of matter and antimatter particles that popped into existence only to annihilate each other upon contact. Left to their own devices, the matter and antimatter inside this plasma should have consumed each other entirely. But scientists believe that some unknown imbalance enabled more matter than antimatter to be produced, saving the universe from immediate self-destruction. Gravity compressed the plasma pockets, squeezing and heating the matter so that sound waves traveling just over half the speed of light, called baryon acoustic oscillations, rippled across their surface. Meanwhile, the high energy density of the early universe's crowded contents stretched spacetime, pulling a small fraction of this matter safely from the fry as the universe inflated like a balloon. The standard story goes that ordinary matter, which interacts with light, congealed around clumps of invisible dark matter to create the first galaxies, connected together by a vast cosmic web. Initially, as the universe's contents spread out, its energy density and therefore its expansion rate decreased. But then, roughly 5 billion years ago, galaxies began to recede once more at an ever faster rate. The cause was another invisible and mysterious entity known as dark energy. The simplest and most popular explanation for dark energy is that it is a cosmological constant, an inflationary energy that is the same everywhere and at every moment, woven into the stretching fabric of spacetime. Einstein named it lambda in his theory of general relativity. As our cosmos grew, its overall matter density dropped while the dark energy density remained the same, gradually making the latter the biggest contributor to its overall expansion. Added together, the energy densities of ordinary matter, dark energy, and energy from light set the upper speed limit of the universe's expansion. They are also key ingredients in the lambda-cold dark matter, LCDM, model of cosmology, which maps the growth of the cosmos and predicts its end, with matter eventually spread so thin it experiences a heat death called the Big Freeze. Many of the model's predictions have been proved to be highly accurate, but here's where the problems begin. Despite much searching, astronomers have no clue what dark matter or dark energy are. As Ofer Lahav, a professor of astronomy at University College London who is involved in galaxy surveys of dark energy, said, "Most people agree that the universe's present composition is 5% ordinary atomic matter, 25% cold dark matter, and 70% dark energy. The embarrassing fact is we don't understand the last two of them. But an even greater threat to the LCDM model has materialized. Depending on what method astrophysicists use, the universe appears to be growing at different rates, a disparity known as the Hubble tension. Methods that peer into the early universe show it expanding significantly faster than LCDM predicts. Those methods have been vetted and verified by countless observations. Therefore, as Nobel Prize-winning astrophysicist Adam Rees, who led the team that made the new James Webb measurement, said, "The only reason that I can understand at this point for them to disagree is that the model that we have between them is perhaps missing something. Measuring the universe's expansion takes a little more than a radar gun." The first method to measure this growth looks at the so-called cosmic microwave background, CMB, a relic of the universe's first light produced just 380,000 years after the Big Bang. The imprint can be seen across the entire sky, and it was mapped to find a Hubble constant with less than 1% uncertainty by the European Space Agency's Planck satellite between 2009 and 2013. In this cosmic baby picture, the universe is almost entirely uniform, but hotter and colder patches where matter is more or less dense reveal where baryon acoustic oscillations made it clump as the universe exploded outward. This soap bubble structure ballooned into the cosmic web, a network of crisscrossing strands along whose intersections galaxies would be born. By studying these ripples with the Planck satellite, cosmologists inferred the amounts of regular matter and dark matter and a value for the cosmological constant or dark energy. Plugging these into the standard model spat out a Hubble constant of roughly 67 kilometers per second per megaparsec. Let's pause on this number for a moment. If a galaxy is at a distance of 1 megaparsec away from us, that means it will recede from us and us from it at 67 kilometers per second. At 20 megaparsecs, this recession grows to 1,340 kilometers per second and continues to grow exponentially from there onward. If a galaxy is any further than 4,175 megaparsecs away, it will recede from us faster than the speed of light. A second method to find this expansion rate uses pulsating stars called Cepheid variables. Dying stars with helium gas outer layers grow and shrink as they absorb and release the star's radiation, making them periodically flicker like distant signal lamps. In 1912, astronomer Henrietta Swan Leavitt found that the brighter a Cepheid was, the slower it would flicker, enabling astronomers to measure a star's absolute brightness and therefore gauge its distance. It was a landmark discovery that transformed Cepheids into abundant standard candles to measure the universe's immense scale. By stringing observations of pulsating Cepheids together, astronomers can construct cosmic distance ladders, with each rung taking them a step back into the past. It's one of the most accurate means that astronomers have today for measuring distances. To build a distance ladder, astronomers construct the first rung by choosing nearby Cepheids and cross-checking their distance based on pulsating light to that found by geometry. Wendy Friedman, an astrophysicist at the University of Chicago, said the next rungs are added using Cepheid readings alone. Then astronomers look at the distances of the stars and supernovae on each rung and compare how much their light has been redshifted, stretched out to longer, redder wavelengths as the universe expands. This gives a precise measurement of the Hubble constant. In 2019, the method was used by Rees and his collaborators, who trained the Hubble Space Telescope on one of the Milky Way's closest neighbors, the Large Magellanic Cloud. Their result was explosive. An impossibly high expansion rate of 74 kilometers per second per megaparsec when compared to the Planck measurement. However, Hubble lacked the necessary precision for the crowded regions of space the team was studying, causing some distant Cepheids to blur into neighboring stars. Dissenting cosmologists had some room left to argue that the result, however shocking, could have come from a measurement error. So when James Webb launched in December 2021, it was poised to either resolve the discrepancy or cement it. At 6.5 meters wide, Webb's mirror is almost 3 times the size of Hubble's, which is just 2.4 meters wide. Not only can James Webb detect objects 100 times fainter than Hubble can, but it is also far more sensitive in the infrared spectrum, enabling it to see in a broader range of wavelengths. By comparing Cepheids measured by James Webb in the galaxy NGC 4258 with bright type Ia supernovas, another standard candle because they all burst at the same absolute luminosity in remote galaxies, Rees and his colleagues arrived at a nearly identical result, 73 kilometers per second per megaparsec. Other measurements, including one made by Friedman with the Hubble Space Telescope on the rapid brightening of the most luminous tip of the branch red giant stars, and another with light bent by the gravity of massive galaxies, came back with respective results of 69.6 and 66.6 kilometers per second per megaparsec. A separate result using the bending of light also gave a value of 73 kilometers per second per megaparsec. Cosmologists were left reeling. According to Ranjan Kai, a cosmologist at the University of California, Merced, who has been working to explain the Hubble tension, the CMB temperature is measured at the level of 1% precision and the Cepheid distance ladder measurement is getting close to 1%, so a difference of 7 kilometers per second, even though it's not very much, is very, very unlikely to be a random chance. There is something definite to explain. The new result leaves the answer wide open, splitting cosmology into factions chasing staggeringly different solutions. Following the Hubble Space Telescope result, An official attempt to resolve the issue at a 2019 conference at the Kavli Institute for Theoretical Physics, KITP, in California only caused more frustration. As the late Vera Rubin, who discovered evidence for dark matter, said at the time, nobody wanted to let go of their pet theory. The split in the community has only deepened since then. Many cosmologists now wonder if the problem is simply that our model is incomplete, but there are other possibilities. Some physicists argue that the discrepancy could be due to new physics not accounted for in the current model, while others suggest there could be hidden factors affecting the measurements. For example, dark energy might behave differently than we expect, or dark matter might have properties we haven't yet discovered. New theories may be needed to resolve this puzzle, and it's possible that the universe is revealing itself in unexpected ways. The James Webb Space Telescope has not only provided new data, but has also opened up new questions about the fundamental nature of reality. As we await further investigations and observations, one thing is clear: the Hubble tension is far from resolved, and the quest to understand the universe's expansion rate continues to challenge our deepest understanding of cosmology. As the debate over the Hubble tension continues, it's important to explore the broader implications of this cosmic conundrum. The discrepancy in the expansion rate of the universe not only challenges our current cosmological models but also invites us to rethink fundamental aspects of physics and the universe itself. One potential implication of this tension is the need to reassess our understanding of cosmic inflation, a theory that describes the rapid expansion of the universe in its earliest moments. If the current model of inflation does not align with the new measurements, it might suggest that inflationary theory requires modifications or an entirely new framework. Another area of inquiry relates to the behavior and nature of dark energy, the enigmatic force driving the accelerated expansion of the universe. The concept of dark energy as a cosmological constant, a uniform, unchanging force throughout space and time, has been a cornerstone of modern cosmology. However, if the expansion rate is not what we predicted, it could indicate that dark energy is not constant but instead varies in time or space. This possibility would significantly alter our understanding of how the universe evolves and how dark energy influences its fate. In addition to dark energy, dark matter remains a profound mystery. The discrepancy in the expansion rate raises questions about the nature of dark matter and its role in the formation and evolution of cosmic structures. Some theorists propose that dark matter might interact in ways we have not yet observed, potentially through new or exotic particles that do not fit within the current framework. If dark matter has properties we have not yet discovered, it could provide crucial insights into the universe's expansion and overall composition. The precision of measurements made by observatories like the James Webb Space Telescope underscores the need for continued advancements in observational technology. Future missions and instruments will be critical in refining our measurements of the Hubble constant and other cosmological parameters. For instance, upcoming surveys planned with next-generation telescopes, such as the Nancy Grace Roman Space Telescope, aim to provide even more precise measurements of cosmic expansion and the distribution of galaxies. These new observations could help reconcile current discrepancies or reveal entirely new phenomena. Cosmologists are also exploring alternative theoretical models to address the Hubble tension. One such model is the concept of modified gravity, which proposes that the laws of gravity might differ from those predicted by general relativity on cosmological scales. Theories like F.R. gravity or scalar tensor theories suggest that alterations in gravitational interactions could explain the observed discrepancies in the expansion rate. While these models offer intriguing possibilities, they require rigorous testing and validation against observational data. The debate over the Hubble constant also intersects with the field of fundamental physics. If the current models are incorrect, it might indicate new physics beyond the standard model. This could involve discovering new particles, forces, or interactions that were previously unknown. Such discoveries would not only reshape our understanding of cosmology, but also have profound implications for particle physics and our knowledge of the universe's fundamental building blocks. Additionally, the Hubble tension highlights the importance of interdisciplinary collaboration. Resolving this issue requires expertise from various fields, including astrophysics, particle physics, and observational astronomy. Collaborative efforts among researchers and institutions worldwide will be essential in advancing our understanding of cosmic expansion and addressing the challenges posed by the Hubble tension. Public interest in cosmology and space exploration has surged in recent years, driven by groundbreaking discoveries and the allure of uncovering the universe's secrets. The Hubble tension, while presenting a challenge, also serves as an opportunity to engage the public with the excitement of scientific inquiry. Educational outreach and science communication play a crucial role in conveying the significance of these discoveries and fostering a deeper appreciation for the complexity of the universe. As researchers continue to grapple with the implications of the Hubble tension, the quest for knowledge remains a driving force. The pursuit of a unified theory that explains the universe's expansion and its underlying principles is a testament to humanity's curiosity and resilience. The journey to understand the cosmos is far from over, and each new discovery brings us closer to unraveling the mysteries that lie beyond our current grasp. In summary, the Hubble tension is a profound challenge that extends beyond a mere discrepancy in measurement. It touches upon fundamental questions about the nature of the universe, the validity of existing theories, and the potential for new physics. As we continue to explore and refine our understanding of cosmic expansion, the interplay between observation, theory, and technology will be crucial in resolving this issue and advancing our knowledge of the universe. The journey ahead promises to be both intellectually stimulating and transformative, offering the potential for groundbreaking discoveries that could redefine our place in the cosmos.